Here again, we're going to relate work and potential energy, but instead of gaining potential energy by moving an object up to a higher height, thus gaining potential energy, we can also gain potential energy or give potential energy to an object by compressing a spring and storing that energy in the spring. So let's say we have a spring of spring constant K. Now, typically, we can give it like units of 200 newtons per meter, which means the amount of force required to compress the spring by a certain distance. So in this case, that would mean that you would need a 200 Newton force to compress the spring 1 meter. So K is simply the ratio of the force required to compress the spring x distance. Now, that means that the more you want to compress the spring, the more force is required. So as you compress in the spring, your force cannot be constant. Your force has to vary. Your force has to increase over time. And not over time, but increase as the spring is more and more compressed. So if we think about it in terms of F versus X, you can see that it's a linear relationship. That linear relationship, of course, is K. K would then, of course, represent the slope of that line. If you rearrange the equation, you could write this as F equals Kx. So you can see that K becomes the slope of that line, but it does show that the force is not constant. It increases as the spring is compressed a greater and greater distance. All right, so how do you now calculate the work done? Well, normally you would say that the work done is equal to force times distance, and of course these are vector quantities. And notice that the force is to the left, the displacement is to the left, so they're both in the same direction, and so therefore you expect that to be a positive quantity equal to the magnitude of F and the magnitude of D. So work is equal to F times D. The problem is that F is not constant, and because of that, we cannot use this equation to solve that. We have to go to a differential equation. So what we can do instead, we can say, let's cut it down into infinitesimally small little segments. Let's say we're going to move the spring from this distance to an infinitesimal distance further along, which is a certain amount of dx. So we're going to compress the spring a very minute amount of dx, and when we do that, the force will change in such a small way that we can ignore that particular change. So we can write it as the dw is equal to the force at that moment in time times the displacement dx. And then realizing that F is a function of x, we can then take this and plug it into our equation right here. So we can write that dw is equal to k x dx, and now we can go ahead and integrate both sides of the equation. Of course, k is a constant, so we can write the integral of dw is the integral of x dx, and then if we integrate that, we have the work done to compress it a distance d is equal to k times x squared over 2. X, of course, representing the amount of compression of the spring. And so the most traditional way of writing this equation is that the work done to compress the spring is 1/2 kx squared. Now, what does that work do? Well, if we assume that there's no loss of energy due to overcoming friction, which with a spring is pretty well the case, then we know that all of that work was then used to put energy into the spring. And since the spring is not moving, it's not kinetic energy, so we can say that must therefore be potential energy. So by definition then, the potential energy gained by compressing a spring must be equal to the work done to compress the spring, so must equal to 1/2 kx squared, and that is indeed the case. So that's how we can figure out how much energy is stored in a spring by compressing it. Now, if we assume that the K is 200 newtons per meter, and let's say that the displacement is equal to, let's say, 50 centimeters, which is 1/2 meter, then let's go ahead and find out how much energy is stored in that spring. So in this case, the potential energy would be equal to 1/2 times K, which is 200 newtons per meter, times x squared, which would be 0.5 meters, and that would be squared. And so 0.5 squared is 0.25, divided by 2 is 1/8. That would be 200 divided by 8, which is 25. So the potential energy stored in the spring would be 25 Newton meters. Of course, that is equal to joules. So that's how we figure out how much energy we can store, potential energy we can store in a spring. So the previous example was potential energy gained by gaining height when a mass is lifted up and given potential energy that way, or we can get potential energy by compressing a spring. In the next example, we're going to show you how to calculate work done, then converting that work into kinetic energy. Right?